The objective of this video is to introduce operational amplifier realization of transfer functions and outline how this can be used for closed-loop regulation of power converters. So basically, we're going to finally come up with a circuit that creates the transfer functions we've been plotting Bode plots of. So in a previous video, we talked about how you can go from a Bode plot to a transfer function mathematical equation. That is a Laplace equation of poles, zeros, inverted poles, and inverted zeros. Now we're going to go from that Laplace equation to a physical circuit that can be used to create it in a voltage signal. And why are we interested in voltage? Well, that is the language of electrical engineering. That is how we can implement our feedback regulator for our power converter, is by measuring a signal, so maybe we're measuring current, converting that to a voltage, and then designing an analog circuit that can manipulate that to be the transfer function, to give us a regulator response to an error signal, that is the difference between an input reference and the measured quantity. When it's time to implement your transfer function, when you've got your transfer function written in terms of your poles and zeros and you want to implement it, you have two basic options. You can either do this as an analog circuit like we just described, or these days it's become very popular to use microcontrollers or FPGAs or DSPs to implement it digitally. In this class, we're going to talk about a simple op-amp circuit realization of a transfer function because it's something that we can discuss in a lecture. And it's also something that you can easily build on a breadboard in the labs. There are many different ways to realize this in terms of an analog circuit. We're picking one approach for this lecture, which is fairly simple. As you'll see, it also has limitations. And we'll talk about that as we get further into the video. But for now, let's talk about the inverting op-amp circuit. This is a basic building block that you've learned in your previous coursework on analog circuits, and you may have forgotten some of the basics of it, so we'll spend a few minutes here reviewing it. So I've sketched the circuit below. It consists of an operational amplifier. This is an integrated circuit that you can buy. It has a very high gain, so if you apply a voltage across the negative to positive terminals, you will get a very large voltage on the output. Also in our circuit are two impedances, Z1 and Z2. In the most simple form of the circuit, those impedances are just resistors. And that is our complete circuit. We have a reference labeled here with this arrow, and otherwise we're applying an input voltage and we're observing our output voltage. So now let's talk about the basics of how you analyze this. To analyze it, that is to calculate our output voltage, we assume the following. We're assuming that the gain of our op-amp circuit is large enough so the voltage at our negative terminal is equal to the voltage at our positive terminal. And at first pass, this may not be intuitive for why this happens, so let's consider the case where we've cut this connection right here. So that is, our feedback impedance, Z2, is no longer connected to the negative terminal. If we were to apply a voltage across these terminals, say we apply 0.1 volts, V0 is going to be driven down to a very large negative value. That is, in essence, our assumption that the gain of this op-amp is enormous, so if we apply a small voltage across the terminals, our output voltage saturates. It goes to the voltage rail of the op-amp. And so you can see that in this case, if we apply a positive voltage at the negative op-amp terminal, and then our Vout is pushed to a negative value, you can kind of see intuitively that if you connect this feedback resistor, your gain will cause your op-amp to push on its output voltage so large, so hard, until you actually end up with 0 volts across these terminals. So for analyzing op-amps, we can use a nodal analysis, and to do that we need to make this assumption that the negative voltage terminal is equal to the positive voltage terminal. The second assumption that we make is that there's no current flowing into or out of the op-amp. And this allows us to say that our current I1 at this location is equal to our current I2 over here. And at this point we can derive our transfer function. We can derive our relation between Vout and Vin, because we can note that I1 is going to be equal to the voltage drop across Z1, which is Vi minus 0 volts, because that's the voltage at the negative terminal, divided by Z1. Similarly, we can write an expression for I2 in terms of the voltage at our negative terminal, which is 0 volts, minus the voltage at our output, which is Vout, divided by the impedance in that path. And then we can equate these expressions to solve for Vout. And we get this final expression for our op-amp. We see that it has a simple gain of Z2 divided by Z1. And it's inverting. It has a negative sign in front. That's why it's called an inverting op-amp circuit. We can use this property to realize any transfer function by modifying Z1 and Z2. And remember that Z1 and Z2 are just impedances. So we can make them functions of the Laplace variable S, or functions of frequency, by using inductors and capacitors and resistors. So we realize we create Z1 and Z2 by some combination of resistors, inductors, and capacitors. And in the classical constant gain op-amp, Z1 and Z2 simply consist of resistors. But that is not a function of frequency. So to make this a function of frequency, to add poles and zeros to the op-amp circuit, we introduce inductors and resistors into the impedances. I want to comment briefly on this negative sign here. So it's an inverting op-amp, which means it has a negative sign there. And we're going to address the reason why that is important to us a little later in the video. For now, you can ignore it because we're going to talk about the gain of this circuit, which is the decibels of the absolute value of Z2 over Z1 evaluated at frequency. And so the negative sign doesn't matter at this point. But later in the lecture, you're going to see why it's actually an important feature of this. It allows us to implement more of our feedback regulator than simply the regulator transfer function. Okay, so let's consider an example. Suppose that we have this circuit here. We have previously commented that its Vout is going to be negative R2 over R1 times the input voltage. And I'm saying R2 over R1 because in this case Z2 and Z1 are simply the resistors R1 and R2. So this is the classical inverting op-amp circuit. And suppose that we were to modify this by adding a capacitor in parallel with R2. I want you to tell me, what does the gain plot look like? So does our gain decrease with frequency and then level off? Does it stay level with frequency for a while and then start increasing? Or does it start level and then start decreasing? So do we have an inverted zero, a zero, or a pole? Pause the video, circle one of these, and resume when you are ready. Okay, let's solve for the new transfer function of this op-amp circuit. We can note that our impedance Z1 is simply equal to R1. Our impedance Z2 is now going to be the parallel combination of R2 and the capacitor, which, if you solve this, you end up getting this expression, and that is to say it has a pole at location 1 over C R2. And so now if we plug this into Vout equaling negative Z2 over Z1, we get this expression, which is a transfer function for a pole at the frequency of 1 over C times R2. And that matches this gain plot, where this pole right here is equal to 1 over C R2. We see that we can add a pole to this transfer function, and we could have modified this further by deciding that, hey, maybe we don't want Z2 to become too small at high frequencies. We could actually introduce a resistor in series with this capacitor, and that would add a 0 to this transfer function. So if at first we added a pole, if we added a pole out here by this combination of a capacitor and a resistor in parallel, Now, by placing a capacitor and a resistor in series in parallel with the first resistor, we end up creating a zero. And so you can keep adding more poles and zeros by making this transfer function more and more nuanced. In addition to modifying Z2, we can also modify Z1. So let's consider another example. And so now we've placed an inductor in series with R1, and I want to ask you the same question. What does our gain plot look like? Which of the three options that I'm drawing here does it look like? Press pause and press play when you're ready to resume. So in this case, our impedance Z1 of S is going to be the combination of R1 plus SL, which we can rewrite as a simple zero. Our Z2 impedance is simply equal to R2. And so if we combine these into our expression for the output voltage, which is again a pole, and so we have this transfer function. We've realized this transfer function, where now omega p is equal to R1 over L. So this introduced a pole in Z1, or I'm sorry, it introduced a zero in Z1, which was a pole in our transfer function for the entire system, since we talk about Z2 over Z1. Similarly to our other example, we could say that, well, we don't want this impedance, Z1, to get too large at high frequencies, so we could provide a resistor in parallel with our inductor. And now, all of a sudden, we have added this parallel combination. We've introduced a pole into Z1. So if you think about what's going on here, in the circuit in this example circuit, at very low frequencies, your inductor looks like a short circuit or very low impedance, and your current will easily take this path. As the frequency increases, your inductor starts to look like a higher and higher impedance, and you take your parallel path instead, which is this pole that we've introduced into Z1. And you can make a similar argument for what's going on in our first example. At very low frequencies, our capacitor looks like an open circuit, and our current will take this path. But at high frequencies, the capacitor progressively looks more and more like a short circuit, and our current takes this path. And so there'll be a frequency at which the impedance of the capacitor and the resistor are equivalent, and that's where you end up with a 45-degree phase margin, because a capacitor always has a phase of negative 90 degrees, and the resistor always has a phase of 0 degrees. So this all relates back to the transfer functions we've been working on building up so far. And we've commented now on how you can modify these impedance networks in order to realize a transfer function equation, in order to introduce zeros and poles into these expressions for your output voltage. And I apologize, both of these expressions should be multiplied by your input voltage, or what you could say instead is that it's V out over VI, which is indeed a transfer function. Let's now talk about how we can apply this to regulation of a power converter. And what we're going to do with our op-amp is we're going to replace this portion of the circuit with our inverting op-amp. Only we're going to make a small change. Instead of the positive terminal of our op-amp being connected directly to our reference, it's now going to have our V out star applied to it. And you can see that we've labeled our control voltage, VC, over here, our input reference or output reference voltage right here, and our measured voltage over here. To investigate how this works, let's go back to our nodal analysis. In this case, our negative and positive voltages are no longer equal to 0, so that's V minus and VP. I'm talking about the voltage at this node and the voltage at this node. They're no longer equal to 0 volts. Instead, they're now equal to V0 star. They're equal to our reference voltage. So we can write that the current coming in, so this current expression, is going to be equal to beta V0 minus V0 star over Z1. So what we've done is we've replaced V minus in all of our equations with V0 star. So I1, or beta V0 minus V0 star over Z1, is equal to the current flowing through impedance 2. And if we work with this a little bit, we can get an expression for VC in terms of everything else. And we finally have an expression for our control voltage, VC. If we assume that Z2 over Z1 is very, very large compared to 1, we can simplify this expression as follows. We can say that VC is approximately equal to... So what we did was we said that this term right here was negligible because we're assuming that Z2 over Z1 is very, very large. And when we do that, we get the following expression for VC. And we can recognize from this expression that this first term is just the error in our block diagram up here. So our error is equal to V0 star minus beta V0, and that corresponds to this first term right here. The second term over here is equal to our regulator transfer function. So again, going back to our block diagram, VC at this point is going to be equal to our regulator transfer function times epsilon. So in other words, VC is equal to the regulator transfer function times epsilon. So by this assumption, we can see that we can manipulate Z2 and Z1. We can add resistors, inductors, and capacitors to our op-amp feedback network in order to implement a regulator. And so this is a key point. This is a takeaway message from the control unit so far. We've just shown you how you can take a simple op-amp circuit, add resistors, inductors, and capacitors to it in order to implement any regulator transfer function that you would like to implement. To wrap up, I want to draw how our complete circuit will appear below. So I'm going to draw the op-amp regulator, our PWM interface, our gate driver, and our power stage or our buck converter all connected together. So starting at the very left, we'll have our feedback quantity, beta V0, and we'll connect this at the end to the output voltage of our buck converter. Right here we have our op-amp regulator, or another word for this is an error amplifier. It's amplifying the error of our circuit. And the output of that is a control voltage, which goes to a pulse width modulator interface. So here I've drawn the comparator, and down below we've got our triangle waveform for the pulse width modulator with a peak of V peak. This outputs a gate signal. So above we've been indicating that the output of our PWM stage is a duty ratio, and that is the block diagram version of what our circuit is. However, in all actuality, the output of our PWM interface is an on-off binary gate signal that goes to the gate of our MOSFET. And in this case, we'll send it through a gate driver. The gate driver isolates the gate signal so it can be connected to the gate of a MOSFET, and it also amplifies the signal to have the correct voltage levels that are needed to turn on and off our MOSFET. There's a throw voltage source here somewhere that we're not drawing. So now we get our single pole double throw converter. We've attached it to an inductor. Perhaps we have a filter output capacitor and some kind of load resistor where our output voltage appears at. And so then we can measure our output voltage and implement a gain of beta by using a voltage divider, and then feeding that voltage back into our circuit. And so this shows the complete picture of our regulator system. So we've got our error amplifier, we've got our pulse width modulation stage, we've got our gate driver, We have our power stage, which is our single pole double throw converter. We've got a load resistor. And then we have our measurement system over here. I want to remark on one other design-oriented detail. We've said that this equation for our error amplifier is true only when Z2 divided by Z1 are much greater than 1. So that is the caveat to this simple approach that I've just shown you for implementing the transfer function, that you have to have this equal to Z2 over Z1 much greater than 1. There are other op-amp circuits, for example difference amplifiers, that would not require this but would have more elaborate feedback networks. This simple circuit, you can in fact go buy a part for this which will implement the op-amp alongside a reference voltage all within one IC. In fact, you can find parts that will also add the PWM stage to this as well. So this is a common approach to make this kind of simple circuit work for your regulator design, because as long as you satisfy this criteria, it's a very reasonable and accurate system. Now, this criteria, this Z2 over Z1 needing to be much greater than 1, that provides another design point for how you select your sensor feedback gain beta, for how you select your negative feedback factor. We need beta to be adjusted so that we can implement our op-amp, so we can pick impedance values for our op-amp that within the regulation frequency, within the bandwidth of our closed loop regulator, ensure that Z2 by Z1 is much greater than 1. When we're past the bandwidth of our regulator, we don't really care what this expression ends up being, but within the bandwidth of our regulation, we need to ensure that Z2 over Z1 is much greater than 1. And we do this by selecting a small feedback factor and by choosing large impedances for Z2 and Z1. So in summary, this lecture has introduced you to the op-amp realization of transfer functions and outlined how this can be used for closed loop regulation of power converters. We reviewed a simple op-amp circuit and how to use nodal analysis to come up with a transfer function for the op-amp circuit. We then worked through examples for how you can modify the feedback paths or the impedances of the op-amp to implement a transfer function. And then we illustrated how the op-amp circuit can be used to implement our regulator and our error calculation for our feedback regulator. So we implement this as an error amplifier. We use nodal analysis to show what the output voltage expression is and when it is true. So how it realizes our error calculation and our regulator. And finally, we sketched how the complete system fits together with a power converter, a gate driver, a PWM stage, and a measurement system. So this wraps up the control unit. You are now in a position where you're able to actually implement feedback control or regulation of a power converter using an op-amp. You know everything you need to know, from how to derive the small signal model of your power converter, to how to sketch the Bode plot of the loop transfer function and design a suitable regulator, and then how to extract the transfer function of that regulator from your Bode plot and then realize it with an analog circuit.